Have you ever wondered what's really going on inside an AI's mind? Today, we're diving into a groundbreaking paper from Google DeepMind that found a way to not just peek inside an AI's thought process, but to actually take the wheel and steer it. Let's get right into it.
We see large language models perform these incredible feats of problem solving pretty much every day. But the how, the actual messy step-by-step reasoning that gets them from A to B, that's always been a huge mystery. How does an AI really think?
For the longest time, their internal workings have just been a complete black box. We see the final answer, sure, but we miss the entire journey. All the logical leaps, the dead ends, the little moments of self-correction that are happening under the hood.
Okay, let's get into the nitty-gritty here. The first big hurdle is that you can't just easily see or even define all the different ways an AI might think its way through a problem. It's not some simple, straight line of logic.
So early attempts to figure this out were pretty limited because they relied on us, on humans. We had to tell the system what to look for, behaviors we could already name like reflection or backtracking. But that's slow. And honestly, what if the AI is using strategies we haven't even thought of?
And this brings us to the really cool part, the solution proposed in this paper, a framework they call RISE. You can think of it like a master key for that black box. And the best part is, it works without us having to tell it which lock to pick.
RISE is an unsupervised method, and that right there is the magic word, unsupervised. It doesn't need any human labels. It's designed to automatically sift through all the noise of the AI's internal state to find what the paper calls reasoning vectors, these pure, fundamental components of thought.
So how in the world does this actually work? Let's break down the method step by step, because really understanding this process is the key to seeing why this is such a huge breakthrough.
All right, so first, the researchers get the AI to think out loud by having it generate these really detailed, step-by-step solutions to problems. Then they chop up those solutions into individual sentences, or what they call thought steps. And for every single one of those steps, they take a snapshot of the model's internal brain state, its activation.
Now, this is where the magic really happens. All those complex activation snapshots get fed into a special kind of network called a sparse autoencoder, or an SAE. The absolute best way to picture an SAE is to think of it like a prism. But instead of splitting white light into its component colors, the SAE is designed to split a complex thought signal into its fundamental building blocks.
And this image here illustrates it perfectly. The SAE takes that jumbled, messy internal state of the language model and basically forces it to break it all down into a small, clean set of core components. It separates that complicated signal into pure, primary behaviors.
And what comes out the other side of this prism? You get these reasoning vectors. Each one represents a specific, isolated, cognitive behavior, a pure direction in the AI's thought space. So all of a sudden, we have these individual vectors for things like reflection, where the model is checking its work, or backtracking, where it decides to scrap an idea and try a new path.
All right, so let's get to the results, because this is where it really starts to get wild. It turns out you can not only see these behaviors, but you can actually reach in and control them. And you can even find behaviors you didn't even know existed in the first place. Take a look at this map. When the researchers plotted out all the reasoning vectors the SAE found, they discovered something incredible. Similar behaviors just naturally clumped together. You can literally see these distinct little neighborhoods for things like reflection and backtracking. This was the proof that the SAE was finding real, meaningful structure inside the AI's mind, not just some random noise.
Now this part is just mind-blowing. Once they identified the specific vector for reflection, they could basically turn a dial on it, amping it up or toning it down in real time. Just look at the difference here. If they suppress the vector, you get a quick, straight-to-the-point answer. But if they amplify it, the model becomes deeply self-reflective, constantly second-guessing and double-checking its work. And the crazy thing is, this is all done on the fly, no retraining required.
And this control isn't some one-off party trick. It's remarkably robust. They found that turning these behavioral dials up or down works consistently. It's effective across different AI models, and get this, the vectors they found for solving math problems even worked when they applied them to completely different tasks, like common sense reasoning.
So if we can find and control behaviors we already kind of knew about, what's the next big question? Well, can we find new ones that we haven't even defined? The answer, it turns out, is a definite yes.
By looking for vectors that seemed to reduce the model's uncertainty, they discovered what they called a confidence vector. And just look at the effect this has. The word cloud on the left shows the model's normal vanilla output. You see these hesitant words like think and perhaps. Then on the right, after they apply the confidence vector, those words basically vanish, and they're replaced by numbers and words of direct calculation.
So, what's the big takeaway from all of this? Let's bring it all home. The conclusion of this research points to a massive step forward for AI safety, for our ability to interpret them, and our ability to control them. This isn't just some academic exercise. The paper really makes 3 huge contributions. First, it gives us this unsupervised framework, RISE, to map out the cognitive landscape of an AI without needing us to label anything. Second, it proves that we can use that map to directly and selectively control how an AI reasons, on the fly. And third, it shows we can use this whole process to discover entirely new cognitive patterns that we didn't even know to look for. The implications here are just profound. This research is genuinely starting to crack open that black box. It's a critical step toward AI systems that are more interpretable, which lets us figure out what went wrong when they make a mistake. It makes them more controllable, so we can align them better with what we actually want them to do. And ultimately, it just makes them more trustworthy, because we can finally begin to understand how they think, not just what they spit out at the end.
Speaking of upgrading thought processes, if you want to upgrade your own brain with more explainers just like this one, you know exactly what to do. Hit subscribe on the VibeDoc channel, because unlike an LLM, your support doesn't need a steering vector to be overwhelmingly positive.
And that leaves us with one final thought. What really becomes possible when we can precisely conduct the thought process of any AI, steering it towards more reliable, safer, and more effective reasoning? Thanks so much for watching.